Hi, my name is Bongkan Jaktranon. I'm a researcher at the National Nanotechnology Center, which is a part of NSTDA. So today I'll be talking about the CCUS activity at NSTDA, specifically on the topic of electrochemical CO2 reduction. Before we started, just a little bit of background on NSTDA itself. So NSTDA is the National Research Institute in Thailand, located in Pathum Thani, 40 kilometers north of Bangkok. Within NSTDA, there's 6 sub-institutes. And the place I'm working in right now is National Nanotechnology Center. So my research group is one of the 5 research groups within nanotech. We are called nanocatalysis and molecular simulation, or Incast. Within Incast, we also have 3 sub-teams. So we have Catalyst Research Team, which are experimentalists working on the development of materials and catalysts for chemical transformation. We serve mostly industry, chemical industry, in order to develop a new process for them. We also have nanoscale simulation research team, which are theorists working on the understanding at the atomic level of the catalyst. We also have our new addition of the sub-team is the nanoinformatics and artificial intelligence. These are people who are very good at developing new AI models to serve research applications. So our team consists of about 22 PhDs, 11 masters. We have 6 to 10 postdocs, and 10 or more staffs that come in as a contract short terms. So the theme of our research is under the concept of waste to values. So our work focuses mostly on the transformation of either biomass or CO2 to chemicals. An example of our work that is very kind of well established is the conversion of biomass to activated carbons. This can be used from very simple like filtering, absorption, or down to drug delivery. So we work on many scales for the active carbons. We also work on the fractionation of biomass to lignocellulosic components. For example, cellulose, right? We can make cellulose nanofibers, hemicellulose, and lignin. So we use all of these as feedstocks to make biofuel, biochemicals, and bioplastics. So like I mentioned earlier, the other direction that we are focusing on is the conversion of CO2 to chemicals. So we have been working heavily on the catalysis process to convert CO2 into useful chemicals such as alcohols, ethylene, ethanol, formic acid. We also start working on CO2 conversion to carbon. We also work on the separation of CO2 and the capture process of CO2 using solid absorbent as well. So just a very simple background on CO2 emission. Everyone knows that climate change is real and the effects is apparent right now. Just for a number out there, so Thailand actually emit about 300 megatons per year. We rank the 3rd in Southeast Asia after Indonesia and Malaysia, and our emission is about less than 1% of the global emission. However, these are still significant amount of CO2 emitted into the atmosphere. During COP26 meeting, we have pledged to achieve carbon neutrality with the international support by 2050 and net zero emission by 2065. These are really, really challenging goals. So in order to achieve these goals, the decarbonization strategies must be taken. Of course, the first strategy is to reform forestry. We have to plant more trees, get rid of wasteland, get rid of all the waste that produce methane or nitrous or CO2, etc. We also have to adopt more renewable electricity, and this is ongoing process of conversion from the natural gas power plant to solar farms or wind farm, etc. Another direction is to electrify everything so that we can use the renewable electricity that we produce. And lastly, which I think is the most challenging of them all, is decarbonization of heavy industry. So heavy industry in Thailand, majority of a really large industry in Thailand is petrochemical processing. Of course, this takes in petroleum and process it, right? So it's very difficult to decarbonize this industry. Another huge industry is cement production. Of course, you're burning calcium carbonate and release a lot of CO2. So finding a solution of that is going to be quite tough. So the concept that has attracted a lot of attention, especially in Thailand these days, is carbon capture, utilization, and storage, or CCUS. CCUS is a series of technology that address the transformation of CO2, right, from CO2 source to the sink. So in this picture, in this cartoon showing CO2 being captured using this direct air capture unit, or it can be captured right at the source, point source. The CO2 can then be released and injected into underground. We call this CCS, or carbon capture and storage. This approach are being researched or being explored by the huge petrochemical company here in Thailand. Another direction is to use that CO2 as a feedstock. And the only sustainable way is to couple it with a chemical transformation that utilizes renewable electricity. Because without renewable electricity, this process won't be carbon neutral or less or net zero, or won't achieve net zero. So then electrochemical processes such as an electrolyzer that utilize renewable electricity is a promising method of converting CO2 into fuels and chemicals. So within Incast, we are working with many technologies within the realm of CCUS technology. For example, we work with CO2 capture, making nanomaterial that has a really high porosity and high specificity to CO2 and can capture CO2 and release elsewhere. We also work on CO2 separation using membrane separation, so we can separate CO2 from methane, from methane as a biogas separation. A huge effort for us in our lab is the CO2 conversion by many reactions. The 4 prongs reaction that we are currently exploring is CO2 reforming of methane to syngas. This is at very high temperature, 700 Celsius to 900 Celsius, but this can be done very efficiently and make syngas in a really almost full conversion. The second direction is CO2 hydrogenation to alcohol. So this is heating CO2 up in the presence of hydrogen, and you can make methanol and ethanol out of it. The third direction, which is where I'm focusing on, is the electrochemical CO2 reduction. Together, we can also do it with photo assist, or we can call that artificial photosynthesis, where we use sunlight to drive the reaction. And lastly, our new addition to the team is CO2 conversion to carbon nanomaterials. So my work focus mostly on the electrochemical CO2 reduction effort, and the goals of my research is to combine CO2 reduction with Bio Refinery. So because CO2 can be reduced at the cathode, we basically accepting CO2 is accepting electrons, so it's reduction reaction. And on the opposite side of the electrochemical cells, there would be an oxidation reaction. And the goals of my research is to combine the biochemical oxidation with CO2 reduction. So we can produce CO2 reduced products and biochemicals products at the same time. So the effort within the lab, we have a lot of researchers who are expertise in material development and system engineering. So these are the hands-on electrochemists or material scientists. We also work closely with theorists who use density functional theory to understand what's going on at the surface of these catalysts. What is the reaction mechanism at the nanoscale level? We also work with physicists who develop new characterization techniques, especially in situ characterization technique, to understand right at the surface during the reaction what's actually going on for the materials. So we can combine the experiment with characterization with simulation and create this triangle of research ecosystem to address the challenge associated with CO2 reduction technology. So for CO2 reduction technology, so this is an example of a device. So the device will consist of an anode, which perform an oxidation reaction of water into oxygen or into or oxidize other molecules into a higher value product. On the cathode side, CO2 can be reduced and can produce many chemicals. It can produce CO, can produce formic acid, methanol, methane, or ethylene, ethanol, or hydrogen, etc. The challenge associated with CO2 reduction, two of the greatest challenge is associated with the reaction itself. First of all, if we are interested in products such as ethylene or ethanol, which has higher value and very large market size, these reactions are very complicated. In this equation I wrote here, you can see that 2 molecules of CO2 require 12 protons and 12 electrons, which means there's at least 12 steps of reaction. As shown here in this paper that we published in 2021, this is a pathway of CO2 reduction to ethylene and ethanol. And you can see this plethora of intermediates. In order to achieve high yields of these products, we have to design a really, really specific catalyst and really, really efficient catalyst. So that's one of the R&D directions that we have to take, is to design a better catalyst for this reaction. Another direction for research is to also design a better system, a better device that minimize the resistant loss. So use the least amount of voltage to drive the reaction, and also minimize the mass transfer loss. What do I mean by mass transfer? So CO2, as you can see that CO2 are being reduced and using protons. The source of protons in this case is water. So we want to maximize, or we want to optimize the amount of CO2 and water at the surface of the catalyst. So that's required quite a bit of engineering, cell engineering, electrochemical system engineering. So that's also the direction that we are taking as well. So this is example of our work published recently. This is a catalyst consists of copper and zinc alloy. So in this system, copper is a known catalyst that can make ethylene and ethanol product or C2 product. So product with 2 carbon atoms. And that's because carbon has an ability to basically point this 2 C bond together. We call it dimerization or CC coupling. And that's because copper has an intermediate binding energy of carbon mono species and hydrogen species. However, copper is not the fastest catalyst. It's pretty slow in terms of facilitating the reaction. So we blend in second metal, which is zinc. Zinc is pretty fast CO2 reduction catalyst, but it only makes carbon monoxide. So when we blend the 2 metals together, zinc can perform a CO2 reduction to carbon monoxide and improve the CC coupling process on copper. Additionally, zinc can also change the electronic structure of copper so that the efficiency of the catalyst is improved. So here shown in this plot is the efficiency or the selectivity of the product. So copper alone make a little bit of ethylene and ethanol, but when we blend in 25% zinc in a form of alloy, we can increase the production of ethylene and ethanol to 30%. So DFT simulation showed that zinc actually changed electronic structure of copper and changed the binding energy of the intermediate, which improved which lowered the energy required to reach the transition states for the CC formation bonds. So apart from catalyst development, we also work on devices. So shown here in this picture, there's 3 types of CO2 reduction devices. So first type of device is a liquid cell. So this is using a solid electrode in electrolyte, which is mostly aqueous solution, and purge in CO2 into the aqueous solution. So dissolved CO2 is being reduced to make product. This system is very easy to make and also quite easy to understand. But the difficult thing is the CO2 solubility limit of in water is very low. So all in all, the rate of reaction is limited by mass transport of CO2 to the catalyst. So the improved version of that is to create this triple phase boundary. We call this a gas diffusion electrode, which is a porous layers of catalyst, which allow water on one side and CO2 on the other side. So at that triple phase between catalyst, CO2 gas, and liquid, that's where reaction happens. So this system would have much higher efficiency compared to this system. And lastly, the final system of all is to replace aqueous electrolyte with polymer electrolyte, which allow the cell to be very close together, the anode and the cathode, so that the voltage loss of the system is very low. So minimize the voltage used in the system. So right now we at the 1 and 2 version of the cell. So right now we're focusing mostly on the second cell type, which we think is really allow us to fully understand what's going on in the cell without being too complicated. So this is an example of the device that we used. So we have both the conventional liquid cell, and we also develop a new flow cells for gas diffusion electrode testing. So as shown here in a CV, a cyclic voltammogram of the performance of the electrode. For a planar electrode in conventional H cells, we can achieve about 20 milliamp per square centimeter. So this is the current. The current is related to the rate of reaction. So the higher the magnitude, the better. So when we transform copper into a gas diffusion electrode, we can increase the current drastically. As you can see in this pink line right here, we can achieve 100 milliamp per square centimeter at voltage less than -1 volts. So that's a huge improvement. This is our catalyst synthesis. So we make catalyst using a simple hydrothermal process. Then we can spray coated the catalyst using this automatic robot that we built ourselves. We get this really nice copper coated on gas diffusion layer. And this is zooming in, you see this nanoparticle and very exact, a very precise size. Then we can test it in our flow cells. And with this system, as you can see, the product is much higher. The CO2 product is much higher, and the CC product is much higher. So the CC product, in this case, we found ethylene acetate, ethanol, and we also found C3 product, which is propanol. So all in all, this reddish color, these are the C2 plus products, and we can achieve greater than 70%. So compared to 30% previously, now we can improve the selectivity of the product. We could also improve the current density, as I showed previously. So all in all, the system is much higher efficiency. So apart from C2 product, we also focus on the carbon monoxide reduction to formic acid. What's interesting about formic acid is that the cost of formic acid per ton is quite high. It could be as high as $800 to $1,000 per ton, which means that when we calculate the techno-economic analysis of this process, CO2 reduction to formic acid could become economically viable and has an edge compared to other chemicals that is the target products. So that's why we are interested in these technology, because then we want to scale it up and actually translate it to a field test and prototype eventually. So our technology shown here in this plot compared to other technology, other papers published, showed quite promising results, quite very good results, high current density and high efficiency towards Formic. And lastly, as I mentioned earlier, my goal is to couple CO2 reduction with Bio Refinery concept. And that arrives from the fact that when we perform typical CO2 reduction, is usually reducing CO2 at the cathode and oxidizing water at the anode. So when we oxidize water, we get oxygen out. Oxygen, okay, it's not the most expensive product, and it's everywhere, right? So making oxygen is not the most economical way of using the energy. So we want to use the energy to oxidize something else that's more expensive. And our target product is FDCA, or furan dicarboxylic acid. So the reason why we are interested in FDCA is the fact that it is a bio-based molecule that can be used to make biopolymers, especially this polymer called polyethylene furanoate, or PEF. So PEF is an alternative to PET, the PET bottle for drinking water, right? PEF is a lot more interesting than PET from the fact that it can be made 100% from plant. It has a higher glass transition temperature, a higher strength, and better gas barrier properties. What it means is that we can make bottle that's thinner using less material, and protect the products or whatever, the drink or the food inside the packaging, so that it lasts longer because the oxygen transfer across the bottle is much less. So that's why this polymer is very interesting. So FDCA can be made from sugar or biomass derivative. And the feedstocks of FDCA is HMF, or hydroxymethylfurfural. And this process can be done electrochemically. So we are, right now we are working on the development of FDCA in large scale. So we can convert fructose to HMF, which is the first intermediate. It has the furan ring and aldehyde on one side and ethanol on one side. And then we can oxidize it using electrochemical system and get FDCA out. So these are the electrochemical process. So we can oxidize HMF continuously to produce FDCA. And this is our lab scale process. We can make about 1 kilo per day, so about 40 to 50 grams per hour. Efficiency is pretty good. The yield is greater than 90%, and it can be stable longer than 60 hours continuously. Then we can use the FDCA produced in this process to make bioplastic or bioplasticizer. So we can produce the furan ester by mixing the furan dicarboxylic acid with alcohol, and then we can create plastic additives. For example, this is a bioplasticizer we use, and we added in PVC, and we found that can improve the mechanical properties and has pretty similar properties to petroleum bioplasticizer. So in summary, we are developing integrated CCU and Bio Refinery concept using an electrochemical route, which means that at the cathode, we're reducing CO2 to either C2 products or formic acid product. At the anode, we are oxidizing HMF to FDCA, which we hope that will be used as a platform chemical to make bioplastic or bio-based plastic additives in the future. So before I conclude, I want to show you guys the faces of Incast people. So this is a huge Incast group, and we have a sub-team. So this is the CCU team. We also have the electrochemical team right here. We also have network with many institutes around the world. For example, Stanford, Helmholtz, Central Berlin, Shanghai University, Kyoto, US, etc. So these are the network that we formed over the years. We also have worked with many of the energy industry in Thailand, for example, PTT, PTTEP, IRPC, the sugar industry, the chemical industry, the electricity producing sectors such as Incast and EA. We also funded by a lot of funding agency in Thailand and abroad, such as Newton Fund, DASTIP. This is the network between Thailand and Japan, Franco-Thai, for example. So with that, I would like to conclude my talk. If you have any questions, feel free to shoot us in email or look us up in the website. So we have Incast website right here. We also have Facebook page and Twitter account as well. So yeah, with that, I would like to conclude my talk. Thank you so much for your attention.